This section examines basic principles of the alternator. The alternator is universally used in automotive applications. It converts mechanical energy into electrical energy by electromagnetic induction. In this simple version, a bar magnet rotates in an iron yoke which concentrates the magnetic field. A coil of wire wound around the stem of the yoke forms part of a circuit with an ammeter that indicates current flow. As the magnet turns, voltage is induced in the coil, producing a current flow. When the north pole is up and south is down, voltage is induced in the coil, producing current flow in one direction. As the magnet rotates and the position of the poles reverses, the polarity of the voltage reverses too, and as a result, so does the direction of current flow. Current that changes direction in this way is called alternating current, or AC. The change in direction occurs once for every complete revolution of the magnet. An alternating current waveform can be shown graphically. This is the waveform of one cycle, that is, one complete revolution of the magnet. It plots changes in EMF against the rotation of the magnet. The value of the induced EMF depends on the strength of the magnetic field. Increasing the strength of the magnetic field increases the value of the induced EMF. It also depends on the speed at which the magnet rotates and on the number of turns of wire on the stationary coil. This simple model has only one stationary coil. This is called single phase. In a real automobile alternator, 3 separate coils of wire or phase windings are common. The windings are arranged so that when the magnet is rotated, it generates a 3-phase output. The phases are equally spaced in time, and this results in a phase shift of 120 degrees. The alternator consists of a stationary winding assembly called the stator, a rotating electromagnet, the rotor, a slip ring and brush assembly, a rectifier assembly, 2 end frames, and a cooling fan. A voltage regulator monitors battery voltage and varies current flow through the rotor field circuit and thus controls the strength of the rotating magnetic field. This keeps system voltage to a safe level. This section examines the rotor. It consists of a coil of wire wound on an iron core and pressed on a steel shaft. An iron segment is fastened on each side of the coil assembly so that the projections or claws interlace. The ends of the rotor coil are connected to insulated slip rings mounted on the shaft, and spring-loaded brushes maintain contact with the slip rings at all times. When a current is passed through the slip rings and the coil winding, it establishes a north and south pole at the ends of the iron core and the shaft. The projections then take on the same polarity as the end of the shaft on which they are mounted, and this forms pairs of north and south poles around the rotor circumference. The rotor usually has 8 to 12 poles, which are tapered to reduce noise as the rotor rotates. This section examines the stator. The stator is mounted between the 2 end brackets. It consists of a cylindrical laminated iron core which carries the 3-phase windings in slots on the inside. The windings are insulated from each other and also from the iron core. They form a large number of conductor loops which are each subjected to the rotating magnetic field. This section examines the 2 end frames. They are normally made from aluminium and form housings to accept the bearings which support the rotor at the drive end and at the slip ring end. Ball bearings are normally used at each end. This section examines the slip ring and brush assembly. Slip rings are normally copper bands molded onto an insulating material, then pressed on the steel shaft of the rotor. Each end of the rotor winding is connected to one of the copper bands, so that as the rotor rotates, the brushes can make a connection with each end of the winding. The brushes are made of a combination of copper and carbon and are carried in brush holders mounted in the end frame. This section examines the rectifier assembly. The diodes for rectification are mounted on heat sinks in packs of 3. One heat sink has 3 positive diodes and the other has 3 negative diodes. The positive diode heatsink is insulated from the frame and is connected through the output terminal to the battery positive or B+ terminal. The negative diode heatsink is connected to the frame, and this allows the return circuit via the battery negative terminal to be completed. This section examines the alternator's cooling fan. This fan is a powerful centrifugal type. It is mounted on the rotor shaft and may be an integral part of the drive pulley or part of the rotor. It is essential to maintain a cooling stream of air over the diodes and stator. This section examines rectification. Automotive alternators use diodes in the rectifier assembly. A diode allows current to flow in the forward direction, but blocks the flow of current in the reverse direction. This is a 3-phase bridge rectifier. It has 6 diodes to rectify the total alternator output, 3 positive and 3 negative. One of each is used to rectify current in each of the 3 phase windings. The positive diodes let current flow out to the battery terminal B positive. The negative diodes complete the return circuit from the battery terminal B negative. In each revolution of the magnet, the polarity of each phase winding changes, and as a result, the current changes direction. To provide a unidirectional or DC output, a complete circuit is needed for current to flow when each change in polarity occurs. Let's look at the action of just one phase. As the rotor turns, it induces a voltage in the winding, which generates current flow. In this position, and with this polarity, the current path is as follows. Output of winding A, positive diode A, alternator terminal B positive, battery positive terminal, battery ground B negative, alternator ground, negative diode B, output of winding B, neutral or star point. When the magnet rotates further to this position, the polarity of winding A changes. The current path then is winding A at star point, winding C, positive diode C, alternator terminal B+, battery positive terminal, battery ground, alternator ground, negative diode A, and output of winding A. As the rotor moves through its various positions, individual phase currents change in magnitude and polarity, but the output current to the battery and the electrical circuits remains unidirectional. This section examines connections of the phase windings. 2 methods of connection can be used for the stator or phase windings: star or Y connection and delta connection. In the star method of connection, One end of each phase winding is taken to a central point where they are connected together. This is known as the star or neutral point. The other end of each winding is connected in the bridge rectifier circuit between a positive and a negative diode. Each winding is then always part of a complete circuit. In the delta method, the windings are connected in the shape of a triangle. Connections are then taken from each point of the triangle to the bridge circuit. This section examines the rotor circuit. Current is provided to the rotor by means of the slip rings and brushes. When the engine is running, most alternators supply the field current directly by means of 3 extra diodes connected to the bridge rectifier circuit. Extra diodes are known as field diodes or excited diodes, and the alternator is said to be self-exciting. However, this self-excitation can only occur when the alternator is producing an output. When the ignition switch is closed, current can flow from the battery positive terminal through the ignition switch and charge indicator lamp to the L terminal of the alternator. The circuit is completed through the slip rings and rotor field winding, and through the voltage regulator to ground on the vehicle frame. The small amount of current flowing in the circuit illuminates the indicator lamp and provides the initial excitation of the field winding. This magnetizes the rotor pole shoes and produces a weak magnetic field. When the rotor is driven by the engine crankshaft, the rotating magnetic field induces a voltage in the phase windings, which is applied to the B positive alternator output terminal. However, this voltage is also impressed on the excited diodes, and current can now flow directly to the field circuit, restricted only by the resistance of the field winding. This strengthens the magnetic field, and the output voltage rises quickly. The voltage regulator now takes over to control the field circuit current and maintain a preset regulated output voltage at the B positive terminal of approximately 14 volts. As the voltage on each side of the charge indicator lamp is now equal, there can be no current flow through the lamp and the lamp is extinguished. The alternator is now said to be charging, and since the output voltage at the B positive alternator terminal is greater than that of the battery, the current flows to the battery to begin the recharging process. This section examines alternator voltage regulation. When the engine is running and voltage output is low, the regulator switches the rotor circuit to ground and maximum current flows through the rotor field winding. The high-intensity magnetic field created raises the value of the induced voltage in the stator windings and alternator output rises. The output voltage is also impressed on the excited diode circuit, and the output voltage is sensed by the regulator control circuits via the regulator L terminal. When the maximum allowable voltage has been reached, the control circuits switch the rotor field circuit off, and the magnetic field at the pole shoes reduces in size or decays. The decaying magnetic field reduces the magnitude of the voltage induced in the stator windings and lowers the alternator output voltage. This again is sensed by the voltage regulator control circuits, and the rotor circuit is switched on once more. The regulator switches rapidly between the on and off conditions, within the preset maximum and minimum voltages, to allow the alternator to maintain an output voltage of approximately 14 volts, and at the same time, deliver the current needed for electrical system operation. As lights and other accessories are turned on and the load on the system increases, the current output to the circuits must be increased and the output voltage must be maintained. The regulator again adjusts the rotor field circuit, but this time increases the current flow and therefore the magnetic field strength. The induced voltage in the stator rises to maintain system voltage and increase current output. There is no need for a current regulator, as the design of the stator winding determines the maximum current output of the alternator at a system operating voltage of 13.8 to 14.2 volts. If an alternator is rated at 40 amps, it is capable of maintaining a system voltage of 13.8 to 14.2 volts up to a current load of 40 amps.